Hi guys, welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on a Taylor cone. This was requested from a subscriber, so thank you for the request, and I'm going to be using a NPH file from COMSOL's application library. There was no tutorial for this, but there was a brief PowerPoint overview telling us about the interfaces we're going to use, so the laminar flow module, the level set module, and electrostatics, and then the multiphysics couplings for two-phase flow. So before we go through that, let's go over the results we're going to plot and what a Taylor cone is. So here's an animation of the results we'll end up with. So you can see this is a liquid phase, and we're forming monodisperse droplets. So that's what's happening in the animation. And here's a pretty good video I found on YouTube. This is from Johnson Laboratory. And you can see, actually let me back up just a second. So I'll pause it here. And you can see that we've got a syringe here, a target over here that we're going to be electrospinning onto. And then you see you've got the red end, so the anode or negative terminal, and then the black end attached to the target or the surface we're going to be spraying, so the positive cathode over here. So you've got a liquid coming out of the syringe, and adding the charge is going to, well, let me just play it from here. So they're going to turn off the light and shine this red light on it to make it a little more obvious what's happening. So flow begins, and you can see just a normal droplet dripping off the end of this micro tip to begin with. And now it's starting to lean. You can see so the voltage in the droplets is building up and beginning to overcome the surface area that you would normally see in this polymer. I don't know what polymer they're spraying. And there you go, the jet is starting to form, and as it stabilizes, you're going to start to see a Taylor cone formation. So it's this characteristic cone shape that comes out of the tip of the injector or tip. And so this is the Taylor cone that we're going to be modeling. And the purpose of this would be to, I think they use it in all kinds of industries, medicine, food, anywhere where you need a very even, thin coating. It also has the advantage of creating surfaces or things with very high surface area, so nanotubes. Okay, so there's our fully stable Taylor cone, and that's what we're going to be modeling today. And there's the end of the video, it's just tapering off back into a drip. Okay, so that's background on electrospinning, why we would be practically interested in the Taylor cone model. And the level set method that we're going to be using is a different way of modeling, so it allows you to track moving interfaces for things like deformities, or in this case we have this very distinctive deformation happening between the two domains. So the level set method is a technique to represent moving interfaces or boundaries using a fixed mesh, as opposed to a moving mesh, which is another way that you could model it, but this is very convenient for certain applications. Okay, so it's useful for problems where the computational domain can be divided into two domains separated by an interface. So in this example here, it's modeling the region at the bottom as this rectangle, and then the two oval and circles have a phi value of 0, and the flat domain has a phi value of 1. And there would be something like a phi value of 0.5 at the isocontour. Okay, so phi is the smooth step function that equals 0 in one domain and 1 in the other. And this allows for the smooth transition between these interfaces, or between these domains, using this equation. So the terms on the left-hand side give the correct motion of the interface, partial of phi with respect to time plus the velocity field vector u times del phi equals the terms on the right-hand side, which are necessary for numerical stability. The parameter epsilon determines the thickness of the region where phi goes smoothly from 0 to 1 and is typically of the same order as the size of the elements of the mesh. So we've got two parameters here that are unique to the level set method. Gamma, which is the, let me check here, reinitialization parameter, and epsilon, the parameter controlling interface thickness. And then here's our smearing function at the end of this parentheses that allows for the smooth to go smoothly from one domain to the other. Okay, and one important note here on those parameters, we talked about eta, or epsilon, equals the largest value of mesh size h within the domain, and the parameter gamma determines the amount of reinitialization or stabilization of the level set function. It needs to be tuned for each specific problem. If gamma is too small, the thickness of the interface might not remain constant, and oscillations in phi may appear because of numerical instabilities. On the other hand, if gamma is too large, the interface moves incorrectly. A suitable value for gamma is the maximum magnitude of the velocity field u. And then you have conservative and non-conservative forms. This is all general information about the level set method, not necessarily applying to our Taylor cone tutorial we're going to do here. So if you want to read more about this, this is in the COMSOL knowledge base. If you just look up, or maybe this might be from a different source. It's the level set method from MIMS module PDF. And yeah, so there is something else on COMSOL's knowledge base about level set method as well. So that's some background information, and since there's no tutorial, I'm going to be creating this from scratch, and I've just gone ahead and used the completed model that they have available in their application library, and just exported the geometry parameters, the parameters for physical properties, and the geometry. So let's start a new file from scratch. Alright, so we're going to do Model Wizard 2D axis symmetric. And the reason for that is because it's a cylindrical model. And then we're going to choose, let's see, oh wait, no, AC/DC. Electric currents, which is under the AC/DC module and under electric fields and currents. And then we're going to add from the fluid flow, expand that, multi-phase flow, two-phase flow, level set, laminar flow. You could also choose turbulent flow for the same level set method within the fluid flow. And there we go, that's all of our physics and then the multi-physics necessary. Alright, and then our dependent variables are going to be u for velocity field, uv and w for each x, y, and z component, and p for pressure. Hit study, we're going to do a time dependent, and you'll notice this with phase initialization appears for anything with level set. Because of our phi function, we have to have a phase initialization as part of the time dependent study. So I'm going to click done. And also you'll see wetted wall, which is unique to level set. So it's any wall that will be an interface between the two phases. So we will also define that. All right, so first of all, let's save it. And then under global definitions, we'll go to parameters, and I'm just gonna import from file Taylor cone parameters here. So you can see in here we've got kappa, the conductivity, sigma, the surface tension, ER liquid, the relative liquid permittivity, rho of the liquid or density, eta liquid or the viscosity, and V naught, the voltage, initial voltage, little vn, inlet velocity, eta air is the viscosity of air, rho of air, and THLS, or the thickness of the level set interface, which is defined as 1 times 10 to the negative 5 meters. So very thin interface for the level set. Okay, so what I want to do is add a rectangle function. So I'm going from the Home tab at the top, choosing Functions, and under Global, selecting Rectangle. So I want to make the lower limit 1 times 10 to the negative 3, and the upper limit 4 times 10 to the negative 3. And we'll use this in the analytic functions 1 and 2, which will be for the applied voltage at the cathode here, and also for the inlet velocity. Baseline 0, amplitude's 1, and we'll reduce the smoothing to 1 times 10 to the negative 3. Nope. Let's go ahead and create a plot of that so we can see what it looks like. So here's our turn off or turn on and turn off regions. And here's what it looks like without the smoothing. So there's our rectangle function. Now we want to add an analytic function, right? So this one's going to be for the applied voltage, V0 times the rectangle function with argument x and units of seconds, which I will talk about later. X is a spatial reference, but time is seconds, so it should be rectangle function of time, right? But COMSOL is weird when you put time and you have to like do something with inverse seconds, or it messes with the default units or something. I don't know. So anyway, we're using argument x. The function for voltage is going to be volts, argument x in units of seconds. And the plot parameters, we're just reducing the upper limit to 5e negative 3 seconds. And we're going to add a second analytic global function. And this one similarly is going to be for Vn times the rectangle, the inlet velocity times rectangle function x in units of seconds with the same upper limit, 5 milliseconds. And this one will have units of meters per second since it's a velocity. And then we also want to add a step function, another final global function. And let's see, the location is going to be at 1e negative 3. Make sure the smoothing, I'm going to also reduce the smoothing from 1/10 to 1,000th. So there's our smoothing function. All right, now we're ready to add our component 1 local variables. So I'm going to select component 1 in the model builder window, go to variables, variables, local variables, and then we're going to add 3 expressions here. So the first expression, epsilon r, epsilon underscore r, our expression for that is going to be 1 plus so it's the relative permittivity of the mixture is 1 plus the relative permittivity of the liquid minus 1 times the level set function VF1 plus the relative permittivity of the liquid minus 1, so that's just the volume fraction of non-liquid phase, so the air, times LS dot VF1. So LS means the level set, it's calling that function, some output of that function, or of that module, level set dot VF1, which is the volume fraction of fluid 1. And then our next 2 variables are going to describe the volume electrostatic force in the radial direction and axial direction respectively. So we've got FES-R and FES-Z. Force electrostatic in the radial direction and FES-Z, electrostatic force in the Z direction, or axial, I guess I could say, axial. Okay, and this is equal to this expression. Half of ES is the electrostatic function, 0.5 times the electrostatic variable ER, or half of quantity, the electrostatic output, ER squared. ER is going to be the electric potential. Okay, so ER is going to be the electric potential in the radial direction squared plus ES, the electrostatic output, EZ, or the electric potential in the axial direction squared, closed quantity, times epsilon naught, our reference permittivity constant, epsilon 0 constant, which I believe was one of our parameters, right? Maybe that's a COMSOL constant. Okay, yeah, that's a COMSOL physical constant. Anything you see underscore constant, C-O-N-S-T, is likely a reserved name in COMSOL. And you can just Google it or look it up in COMSOL documentation. So epsilon naught underscore constant is the permittivity of vacuum, and it's an electrical constant. Well, anyway, it's in units of farads per meter. Okay, so constant times 1 plus quantity, the relative permittivity of the liquid, minus 1 times fills phi LSR. So this is the phi is our variable for the level set, ls is level set, and r means in the radial direction. Okay, and just going to copy this into the next one, FESZ, and then change the just change the last appearance of the phi variable from the R to the Z. Okay, and this is the volume electrostatic force. In the axial direction. Okay, it doesn't recognize ER because it hasn't computed yet, but that should go away. All right, so those are our local variables. And now we're gonna add our materials. So we've got some unknown plasma that we're electrospinning. So we're just gonna create a blank material. And then we've also got air. They've chosen to define rho and eta of air here rather than use the built-in, just to see if it models the same thing for fun. I'm gonna do the air from the built-in library and see if it changes anything. So let's browse materials, air. So we'll just use the built-in for air. And then the other one we will have to create from blank. So let's do a add material. Oh. So I'm going to go to the materials tab and blank material. And then we're going to add these values. So the whole domain 1 and 2. And let's see, relative permittivity is going to be so you can just click on material 2 and at the bottom here fill in the basic material constant. So the relative permittivity is going to be ER liquid, which is one of our parameters, and the density is rho liquid, and the dynamic viscosity is eta liquid. Okay, and for material 2, I know it seems a little bit counterintuitive not to select a domain for the material, but it will use this and it'll reference the material constants of air in the level set module. So the thing is, we have a deforming boundary, right? So technically the liquid is material 2 and this is air to begin with, but at some point the liquid boundary deforms, so it goes into this domain. So we're just defining material 2, or the charged polymer that will be electrospinning through the Taylor cone, as the entire domain 1 and 2, and air won't have any selection. Hopefully that makes sense more as we go. Okay, so we're done with our global and local definitions. We're done with our geometry and materials, and now we're going to move on to defining the physics and mesh. All right, so under electrostatics, we've got all domains selected, 1 and 2. And oh no, I chose electric currents, not electrostatics. Okay, so what I'm gonna do is just delete this. Delete electric currents and go back to physics and add physics, and we're gonna choose electrostatics. So under AC/DC again, electric fields, the one right on top of it, electrostatics. Okay, add to component 1. All right. So there, let's see if I can just drag it up here. All right, there we go. All right, charge conservation. Okay, so the only thing we're changing here is for charge conservation, going to the constitutive relation dE. So we're going to keep this relative permittivity, but we're going to change it from material to user defined and call our parameter, or use our parameter epsilon r. Okay, if we go back to our parameters, we can see, no, epsilon r was that variable. So epsilon r is the relative permittivity of the mixture. So it is changing and then our axial symmetry, it's already pre-selected the appropriate axis there. So that's the axis of symmetry, is the axis about which we're rotating. So if you rotate this rectangular geometry about the z-axis, you get the cylinder. Okay, zero charge is going to be the outside. So the default values we're not changing. Initial values, it's going to start with an initial value of 0 volts until we apply an electric potential. So now we're going to right click on electrostatics and add a ground condition. And our ground is going to be, the ground is going to be this region here. Okay, so what this represents, let's go back to the PowerPoint. What that little notch represents is where that would be the end of the Taylor cone. Yeah. It is our cathode. Okay, so we've got our anode here. This is where, in that video I showed at the beginning, that's where the red, the negative terminal was applied, applying a high voltage here. And this is the cathode, or the outlet orifice. In our case, it's ground. So I guess we just have to think about applied electric field over anode and cathode. I guess it's just how we define anode and cathode. The anode being the region from which electrons are departing, and the cathode being the region to which the electrons are flowing towards. Well, it makes sense that our cathode would be the outlet orifice, because we're charging the particles with the droplets form at the outlet orifice. Then the charge separation happens between the anode and cathode. That's okay. So we've got competing effects between surface tension and the applied voltage to the particles, which overcomes the surface tension. So if we think about it as this is a Debye effect or shielding effect, and it's overcoming the intermolecular forces that cause surface tension. They're both, so we've got van der Waals interactions and the liquid. The liquid naturally has intermolecular forces that make it want to form as a droplet or surface tension. So you have van der Waals force there. And then you also now have injected charge and charge separation. So this is van der Waals forces overcoming the intermolecular van der Waals forces. And it's happening between the anode and the outlet orifice, or the cathode. So we're defining this as ground. All right, and then we need one more thing. What is it? We have to add the application of voltage. Okay, so we're going to right click on electrostatics again and add electric potential. We're adding a positive, so it's going to be this region here. That's our anode, where we've got the negative terminal applied, and it's our applied electric potential is going to be analytic function 1. Okay, so here's what I said I was going to come back to. When we were defining our analytic function 1, what did we say? The argument x is in units of seconds. So actually, it's time, right? X is time, not meters. It's not a spatial, it's a temporal function. But we can't put rectangle 1 function of t, unknown model parameter or physical constant. It has to be a physical constant. And you'll notice you can't change this x here, so it has to be a spatial rectangle function. But it's actually a function of time. As you see when you call it in the electrostatics module, we say analytic function 1 argument is time. I don't know why that is. Someone who's a COMSOL developer could probably explain that better, but it's just kind of a weird thing I've noticed. Okay, so that's it for the, oh, hold up. I didn't define the right region. I'm missing some boundaries here. So it's going to be this entire area, or these, all 4 of these boundaries, 9, 10, 11, and 12 are the anode. Next, we're going to go to laminar flow. And once again, we have both domains 1 and 2 selected. We do want to include gravity so that it accounts for any hydrostatic head pressure. And we're going to choose incompressible, or leave the default incompressible flow, leave these defaults, and then go to fluid properties. And also you'll notice when you hit include gravity, a new node appears in the model builder window under laminar flow with the volume force for the acceleration of gravity. So now we're going to go to fluid properties. We're going to keep the default values here. So the fluid properties apply in both domains. Temperature is from the common model input. Initial values are all going to be 0, but we are compensating for hydrostatic pressure. That's why we've included gravity. Axial symmetry, once again, is going to be the z-axis, or the left side of this rectangle. And wall 1 is only going to be the outlet orifice. But we can't deselect them, so we'll have to add boundary conditions for the other boundaries on this right top and bottom of the rectangle. I'm going to right click on laminar flow, and we're going to add a volume force. So up at the top you see fluid properties, volume force, initial values. So by adding a volume force, we can now fill in the variables we defined earlier. FES, gooey Grammarly, sub R for the R component, and the electrostatic force for Z for the axial component. Finally, for the level set, you always have to have a inlet and outlet as part of the laminar flow model. So let's just go ahead and add both of those and then select them. So, oh, and then I forgot to select the domains for volume force. That's going to be applied to domain 1 and 2. The inlet is just going to be inlet here, and the outlet is going to be up here. All right, now on to the level set. Okay, so level set model 1, our reinitialization parameter, we can keep at 1. Oh, shoot. Okay, so for our inlet condition, we're going to use the boundary condition of fully developed flow. So we're neglecting the startup effects. We've got a fully developed polymer flow here, and we're going to use the analytic function we defined earlier. Analytic 2 is a function of time. In the level set module, we are going to leave gamma at 1, and for the parameter controlling interface thickness epsilon ls, we're going to use the parameter we defined at the beginning, th sub ls, which is 1 times 10 to the negative 5 meters. Thickness, level set. The level set module is really sensitive to these two parameters. I know just from past failure trying to do a level set method on a different modeling for something else entirely. And I couldn't get these right, and there's not a whole lot of documentation on these. So we just have to take it at face value that that's the right value for parameter controlling interface thickness. But if anyone knows more about that or the physical ramifications of these two parameters and how to optimize them, so you don't get runaway solutions that don't converge or that just solve forever with tiny time steps, which has happened to me, please leave it in the comments or leave links to documentation because it would be really helpful. Okay, so initial values of fluid 1 is only by selecting fluid 2 as air. This makes fluid 1 right here, so our starting polymer region, this is all liquid. So fluid 1 has a phi value of 0, which means fluid 2, the air, is going to have a phi value of 1, and the interface will have a phi value of 0.5. And that boundary deforms as the Taylor cone proceeds. Axial symmetry, that's already selected. No flow, so we're going to have to override no flow since these do not apply. So let's right click on level set and choose an inlet and outlet and then select those. So our inlet is going to be down here And this is fluid 1 with a phi value of 0. Outlet's going to be up here. Alright, now how do we override the no flow regions? Because actually the only place we don't want flow is at the outlet orifice. So we're not going to actually add anything to the level set module. We're done with that. But we will correct this with the wetted wall node under multiphysics, which couples the laminar flow and level set moving interface. So the wetted wall is going to be anywhere in contact between the two phases, between the polymer and air. Basically everything except the outlet orifice. Okay, and by selecting these, we can see if we go back to level set, no flow, now these are overridden. Can't forget that tiny little leg on the bottom of the cathode. Go to wetted wall. Technically that is wetted. Okay, and then under multiphysics, two-phase flow, level set 1. For surface tension, we do want to include surface tension, and this isn't a water-air interface, so let's do user defined, and we're going to put sigma here, and that's our parameter for the surface tension of the charged plasma. Or just the surface tension of the plasma droplets, 0.0235 newtons per meter. Okay, and then for the wetted wall conditions, well, I guess it's just the height of the entire tube, since that's where the droplets are forming. I'm not really sure. Anyway, moving on. Okay, so now for the mesh, what we want to do is use a larger mesh in the liquid region and a very, very small mesh in the region where we want the level set occurring. Basically, by that, I'm saying we want to, don't waste all your computation power on the area that's only one phase. We want to have as small a mesh as possible in the area where the level set is occurring, because remember, we're trying to model like droplet level changes in a two-phase interface, so we want very fine resolution there in our meshing. So I'm going to choose extra fine, and then so we're going to have a different mesh here than here. So what we want to do is create a distribution. So under the mesh tab, go to mapped, and then add a distribution, and then we're going to select this boundary. So basically we're going to map this square. So first I'm going to choose this boundary and put 20 elements, and then again do another distribution and choose this boundary and make it 20 again. That's roughly a square, slightly rectangular. And then it's going to be free triangular in the remainder. Oh, I forgot to select the domain. So we only want to map in this domain. So I'm going to change the geometric entity level to domain, and then we have distribution 1 and 2. So it'll just map this as a 20 by 20, 20 elements by 20 elements in that domain. And then for the remainder, we want to go to free triangular. This one, it's fine if we do remaining because there's only one other domain, and it will use the default size for that. Okay, and now we can do build all. There you go. That's actually probably not small enough. Let's try going back to size. Let's do extremely fine and then do build all. Okay, that looks better. So you can see, zooming in, we've got squares and domain 1, and then free triangular on the rest of it. Okay, I think we might be ready to do the study. So let's go ahead. Oh, I think we want to change our output times. Let's see what they used for their time range. Okay, so they did only up to 6.5 milliseconds in increments of 20 negative 4 seconds. Okay, 6.5 e negative 3, 6.5 e negative 3. Because again, we're only generating one droplet, so we don't really need a huge time range here. 1e negative 4. Okay, and let's hit computes. Study 1, compute. And if you want to watch the progress, you can click on progress here at the bottom, and undefined material property row 2 required by two-phase flow, level set 1. One thing I failed to change the default values for. Under the two-phase flow level set 1, which is the first node under multiphysics in the model builder window, we do need to change the fluid properties, because if we just leave the default for domain material, well, it doesn't account for the fact that this domain starts as fluid and this domain starts as air. So we've got to go into domain material and change it to fluid 1 is going to be material. Material 2 is my fluid density from material, constitutive relation, Newtonian, dynamic viscosity from material. Fluid 2 is going to be air, and all of these should be from material. Okay, so let's try this again. Go back to study, compute. So these are stable, which is good, and then you can go to the time step to see how it's resolving. And we've got the time step number versus the reciprocal of the time step. So as this number gets smaller, it means the time step is getting larger. If it shoots up too high, that's not a good sign, because it means your time step is getting too small and it's just gonna stay looping forever. But this is a good stable this is a good sign when you see a time-dependent solver convergence plot that looks like this. You can see our progress is about 63% right now, so it shouldn't take too long. And it looks like we've got some standard outputs here. Electric potential with a surface plot and a streamline plot. Electric potential revolved geometry, volume plot. So there's our 3D output from the axisymmetric computation. And then we've got electric field normal with a surface plot and a streamline plot. Velocity, single phase flow, surface plot, pressure, contour plot, velocity surface plot, volume fraction of fluid, surface plot, and contour plot. And the most important one, or the most interesting anyway, the volume fraction of fluid isosurface plot. So first of all, let's change this from gray to, if we right click on isosurface, we can add a color expression. We want to change the expression to SPF single phase flow output.u, or the velocity in units of meters per second, and plot. Okay, let's just play this and see if it looks anything similar to the one from the COMSOL model. So you can either create an animation or you can just go back to beginning, which is this arrow with the bar in front of it, plot first, and then step through all of the time steps. There you go. So you see the, if we go back a few steps, here's where the charging is starting to invert the droplet surface, so you get that characteristic cone shape. There's our Taylor cone, and here is the orifice outlet or cathode, and this is where the droplet forms. There's our droplets, and there's where it hits the target or disappears from our modeled output range. Okay, so let's compare that to this one. Let's do play on the animation. Let's go to volume fraction of fluid 1. Let's choose study solution 1 and then choose the time from the list here, 0.04 plot. So they use the Aurora Borealis color scheme. So if we change this, okay, there we go. Okay, the reason I had that white line there is because I had it at 0.0065, which is where you do have air separating the rest of the domain, because you've got the dot, the monodispersed droplet has already separated from the initial phase of starting fluid. So when the white line is continuous around this part, like at 0.004 seconds, I just plotted 0.004 seconds. I don't know why this still says 0.0065, because I just plotted it. There's probably a bug with this version or something. So anyway, when the line is continuous, that means we haven't formed a droplet. But as you continue, you can see the droplet separates, and then so the other thing they changed here was just the color. Instead of from theme for the plot dataset edges, they changed it to gray, and that's just for the containing geometry of what would be our syringe and cathode area. What was black, they just made it gray, so it's a little less conspicuous, since what you really care about is the fluid inside. And then the frame, they changed to material instead of spatial. There you go. Let's watch it one more time. Since we did all that work, let's watch the pretty animation. Beautiful. I love it. So this has been a tutorial on Taylor cone using the level set method in COMSOL 6.0, and I hope you enjoyed it and learned something. And if you know more about the level set method, please leave it in the comments, because even though I did this tutorial, I really don't understand level set that well. So if you like this video and you want to see more, please hit the subscribe button and also hit like, and feel free to comment and share with a friend.